So I think when we were going over Chapter 1, I said that it was very dense. Well, actually, this is really very dense. And when in my 100 level geospatial class, the topics that are being presented this week are things that I would spend, I think, 2, maybe 3 weeks going over, and he's got this condensed all in one chapter. So I don't know that any of what I'm presenting, or very little of what I'm presenting, would you actually use in a classroom. But my goal at this point is to get you to be able to edit and adapt data so that your students can use it. And so this is really stuff that you would need to know and kinds of issues that you may run into. So we're just going to go through this. So one of the things that I talk a lot about, and he may mention this too, is this idea of what is spatial data, the idea that it's location based. And one of the themes of location is a relative location and an absolute location. So I spend a lot of time with students talking about that we use relative location all the time. So the bottom example is where it's relative or related to other features. So when I talk about my school, I could say it's so many miles in a cardinal direction of another city, or south of some place. So I use other places or other known features, and then put what I'm trying to describe to somebody or locate to somebody in context or in relationship to that. On the other hand, absolute location is a standalone. I can say my address, and I don't have to say, my address is 90 West 30th Avenue, but I don't have to say, and that is next to 80 West 30th Avenue, or I'm 2 blocks from the Safeway. I might say that. I might give both absolute and relative location. So this idea of spatial data really relies on some kind of absolute location in order to put it on a map. The textbook will go through measuring the Earth very briefly, geographic coordinate systems, map projections, other coordinate systems, and then the lab 2.1 talks about coordinates and measurement. I think it's a little bit shorter than lab 1.1, and I'm sorry, Ashley, that wasn't clear, that the steps. And then I want to go over some aspects of land division systems, and this is the township range system is particular to the United States, but when you're looking at images, these are really critical land divisions or cultural systems that have an impact on the landscape. And so when students are looking at maps, one of the important aspects is being able to read the landscape based on some of these patterns. So the book starts out talking about a datum, and a datum is a model or a system that defines the size and the shape of the Earth. And so over time we've had different datums based on our ability to more accurately or less accurately locate places, and with the advent of satellite surveillance we can get much more accurate information about the size and the shape of the Earth. And so you need to know the size and the shape of the Earth in order to set up a grid system. So if I'm going to set up a grid system, I have to know what is the distance between those grids in order to create an accurate location. So there are lots of different datums, and I think he talks about some of the more common ones that you might see on a topographic map. NAD 27 would be the North American Datum from 1927, and so that's when that measurement system was, or that model of the Earth shape and size was developed, and it's kind of the starting point or the reference grid for setting up your other coordinates. Okay, so let's go back here. So today, I think it was Russ was talking about, so why do I want to know that? That's all very interesting. Well, there's some great examples of why knowing about datums is important, because datums, because they define different sizes and shapes of the Earth, that can be one of the reasons sometimes that data doesn't line up. So I found on the internet an example of coordinates that were taken using one datum and plotted on a map using another datum, which caused the actual lighthouse to be located incorrectly. And so and it can be as much as, I think the example was 207 miles off, or 207 meters off, and that could be significant, especially if you've got a storm or you're navigating blind. So just practical matters, you want to know that you're working in two different datums. There can be transformations that line those up, and we'll do that next chapter. Anyway, and then a review of latitude and longitude. Latitudes are also called parallels. Longitudes are also called meridians. Latitudes, this gets really confusing for students. Latitudes measure distance north and south, but the lines themselves run around from east to west, and they're called parallels because the distance between them is exactly the same. They never cross each other. Meridians, the linear meridian goes from north to south, but they measure distance east to west. So sometimes I talk about longitude lines are longer and latitude lines are kind of like a ladder, and some students that's helpful, some of them they just roll their eyes. So one way to help them think about longitude is that 360 degrees, and if you tilt the Earth and look at it from a polar aspect, that makes sense. You're looking at a 360, and if you talk about boys doing a 360 or cutting cookies or doing a 180, they all know what you're talking about. And probably girls. That was so gender biased of me, but there you have it. Then when you look at latitude, if you do a cutaway of the Earth, and this is from a book that Esri now publishes called Map Use Analysis, and it's a great book, but it's really pretty expensive, so and very technical, so I've quit using it in my classrooms, but I do borrow some of the images. So if you cut away the Earth at the equator, the latitude measures the angle from the equator. So 90 degrees would be a 90-degree angle straight up, and Oregon, Eugene or Salem, Oregon is exactly 45 degrees north of the equator, and so is Fossil, Oregon, which is a very cute place if you've never been there. So then I often have to talk to students about latitude and longitude being a lot like a clock, that there are 60 minutes in an hour, 60 seconds in a minute, and that's the same as 60 minutes in a degree. I think one of the problems of using digital timepieces really makes it hard for students to get that visual connection, or that spatial connection between divisions of degrees. And I also have students work on being able to navigate. So if you travel, if I'm at 10 degrees 58 minutes north and I travel 2 minutes north, what is my new location? And it's really tricky for them to think about not working in a base 10, because they'll often say 10 degrees 60 minutes. So I have to go over that quite a bit to kind of get that through to them. Let's see. I think I skipped a slide, but we can come back to that. So when you think about latitude and longitude lines, latitude is from 0 to 90, because we're talking about 90 degrees from the equator, so straight up. North and south are the hemispheres. And then longitude, we look at either from 0 to 360 if you're talking about the full circle, or you can open up the Earth on a flat trajectory and kind of think of it as 180 degrees to the east and 180 degrees to the west. And because we're doing a lot more with digital formats, using north and south can be a problem, and so that's why we've developed the positive and negative nomenclature instead. So if it's north latitude or east longitude, there are no symbols. But if it's south latitude, there's a negative symbol, and west longitude, there's a negative symbol. Two ways to kind of write that. I just said all that. One thing that students often don't know is that you can make the degree sign by on the number pad holding down the Alt key and typing 248, and they love that. Sometimes I think that's their most favorite thing they learn. And so you can work with the changing location, again, moving minutes and seconds, and it's really interesting looking at moving that students really need to think about. If I'm in the northern hemisphere and moving north, I'm adding units. If I'm in the northern hemisphere and moving south, I'm subtracting units as I move toward the equator, and the same with east-west. So those are really challenging concepts for students. The other thing that's really important, and this is, I have my 100 level students know how to do this. You have to be able to change formats, and yes, there are converters in Google, and I often check my math by using the Google converter, but you need to be able to move from decimal degrees to degrees, minutes, and seconds. So one of the things, I like to collect data in degrees, minutes, and seconds, because it's just a little easier for me to think about distance that way, and yet then I need to convert it into decimal degrees to be able to upload that data into a computer system like ArcGIS or QGIS. I'm pretty sure that Google Earth will take degrees, minutes, and seconds. And then the one I skipped back here, let me see if I can find that again. Yeah, that 1 degree of latitude is approximately 69.2 miles between each degree of latitude, and that doesn't change. That's pretty consistent. But longitude, the distance between 1 degree of longitude at the equator is about 69.2 miles, but 1 degree of longitude at 45 degrees latitude, so halfway up, is 49.93, and that's because lines of longitude converge at the poles. So a degree of latitude and longitude are about the same linear distance at the equator, but as you go toward the pole, halfway to the pole, the distance between 1 degree of latitude would be about half. So, and that's a nice way for students to just kind of think about changes as you move together. And it's also why a lot of topo maps in the northern hemisphere are not square, even though they're all 7.5 minutes coverage. Okay, so he goes into some really basic ideas of projections, and excuse me, one of the things that's really important to know when you're trying to add data and get data, especially when we go into QGIS or ArcGIS, is that if you just have data that is in a geographic coordinate system, the data has not been transformed to adjust for the curvature of the Earth. And so when I am mapping Oregon, if I use a geographic coordinate system as the and it's not projected or it's not transformed in any way, Oregon looks very misshapen. So there are projections that help maintain either the accuracy or the shape or the direction of the physical space that you want to map. And so it really depends on what area you want to map as to what kind of projection or projected coordinate system that you will use. And so sometimes when you go into QGIS, the data that you get off the internet is unprojected data. It's in a coordinate system called WGS World Geographic System 1984, WGS 84, which means that many of the, when you look at the United States, it's kind of elongated. east to west. And so sometimes if you have data in two different projections and data that's unprojected, your map layers don't talk to each other correctly. And so that's something that we'll talk about a little more. But it's one of the reasons that projections are important and included in basic mapping classes. So two kinds of projections that we're going to use in the state plane coordinate system and the universal transmercator are the Lambert conformal conic and the cylindrical projection. And the Lambert conformal conic or conic projection is kind of what it sounds. It's as if you created a cone, laid it over the surface that you want to map, and the areas that actually touch the cone are less distorted than the areas far away. And I have a resource that I'll show you in a minute that is very interactive, and I use that for students also. So the state plane coordinate system is a location system that was developed to map smaller areas, not statewide, but smaller areas. And in the United States, each state has its own set of state plane coordinate systems. So, for example, in Oregon, we have a north state plane and a south state plane. In California, you can see there 1, 2, 3, 4, 5. They have 6 state plane systems. In Texas, 1, 2, 3, 4. They have 5. And that way, if you're mapping just a smaller area, you don't really have to be as concerned with the curvature of the Earth because it's being spread over such a much smaller space. So if I'm mapping an area that is more linear north-south, then the map will use the transverse Mercator projection. If I'm mapping data that has more of an east-west extent, then the map or the map uses the Lambert conformal projection. So and so instead of north, south, east, and west, UTM and state plane systems use all positive numbers, and they have what's called oh man, I just lost it. A central meridian and 2 parallels. So if you think about where the map touches the parallel, or the parallel is the paper that actually touches the globe, and that aspect is much more accurate. And the further you go north or south of those parallels, you get a less accuracy. So if Pennsylvania is divided into a northern zone and a southern zone, and there are 2 parallels that are created, and measurement begins way south of the north zone, and that way they can measure everything north as called a northing. And they also set what they call a false easting that is way over here off the area of Pennsylvania, and so that everything they measure is east of the origin. So you don't have to go north, south, east, and west. Everything is a northing or an easting based on this false starting point. They are often in feet. This one happens to be in meters. And so the way that these are recorded is how many meters east of the origin and how many meters north of the origin is the location point. And I think in some ways it's easier to see that with UTM. So state plane is used in the US. Each state has their own zones. The UTM system was developed for a global grid system, and the Earth is divided into 60 zones, and each zone is 6 degrees wide in longitude. So Oregon is in zone 10, and between 126 and 120 is 6 degrees of longitude. And so the way this works is you take these gourds or these panels, and in the northern hemisphere the equator is the origin, so everything is north of the equator in the northern hemisphere up to 500,000 meters north. And then they set a false easting outside of that zone, and everything that's mapped is east of that origin. And in the middle there is a central meridian. And so the UTM uses the transverse Mercator projection, and that means that anything running along this line is more accurate, and it becomes less accurate as you move away from that tangent line or that line of contact. And so I've got some interactive links I can give you that will help with that. So then the three land division systems are meets and bounds, French long lot, and the public land survey system. Those are the three major land division systems in the U.S. And so the meets and bounds is probably the oldest land division system. It's based on the system that was commonly used in Europe, and you see this in the original colonies. So you'll see that more in the northeast part, a little bit in just the general east part of the United States. So if I look at a map, you're going to see meets and bounds predominantly in this area, a little bit in Texas, although in Texas you see a lot of the Spanish land grant system as well. So meets and bounds is based on landmarks. So it's described as distance and direction from physical features. And this also led to very irregular shape that led to people grabbing, early settlers or early migrants grabbing the better land, out of the floodplain, better slope, better aspect, and it creates this really kind of patchwork quilt landscape that's just so visible in Google Earth. When you look at French long lot, that is this this system of trying to have equability. I'm done here. Anyway, trying to divide the land so that people have equal access to water, to transportations, to sloping land, to more fertile land. And so over the years, this subsequent division of land, these slices of land get narrower and narrower. It's also called, I think, the French apparent land division system. And you see that in the United States, in the Northeast, Canadian border, and a little bit in Louisiana. And this is a bad choropleth map. I would point that out to students. And so from Google Earth, you can really see some of these landscapes. So this is a way I use this to talk about land division, describing patterns, and then I have students use township range, or not township range section. What is it I'm thinking here? The Google Maps markup, place marks, to identify different types of land division systems. And then I often ask them about how that's impacted the growth of the city or the development of roads and things like that. The final land division is called the PLSS, the Public Land Survey System, which is based on the Land Ordinance of 1785. And again, this idea that if you're mapping smaller spaces, you don't have as much curvature to deal with. And so the western states were divided into specific baselines and meridians, grid system. And so in Oregon and Washington, there is what's called the Willamette Meridian that runs from northern Washington down through Oregon, and then a baseline that runs actually through Portland, and a grid system using that origin was developed, and then the township range and section then evolves into 6 miles by 6 mile grids, and each of those grids is divided into 1 square mile, and each of those can be subdivided. And so it's a really common way for resource managers and resource departments like the Forest Service or the BLM and a lot of historic land deeds to divide up parcels or to talk about land parcels. So anyway, that is that. So what I just wanted to show you briefly, and I'll put this as a paper as well so you can have better access. But there's just some readings, things that explain the PLSS system, a great explanation of projections, and then I have a list of games and practice sets. But Penn State has 3 really nice little apps that help you practice latitude and longitude, UTM, and looking at, let's see if I can open this. You're not going to open Hyperlink. Looking at projections and how they change shape or other aspects, shape, area of, I'm going to try this way, of the landscape. So let me try. Okay, so here is their little projection tool, and I often have students kind of describe what's happening when they look at the map here. Oh, let me see, there should be circles somewhere. I want to view the distortion ellipses. So they have these circles that were originally all the same size and same shape, and you can see that as I change my projection. So let's look at the Lambert projection and redraw the map. You can see that the circles stay the same shape. So the Lambert projection doesn't affect the shape, but it does affect the size. And so the further I get on the edge, the more distorted or enlarged the sizes are. So this has just been a really nice way for students to get a visual sense of the map. So here's the Mercator projection. Again, the shape is fine, but you can see how much distorted the northern and the southern aspects of this map image are based on this projection. So as I said, that's a huge amount of stuff, and I think the book covers it very briefly, and I probably didn't cover it in much more detail, but a lot of resources to help you if you need it on this.